Hello, everyone. Thank you for joining us today. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's webcast. Today we have Michael Snoyman presenting Designing Domain-Specific Languages with Haskell. Michael is the author of the best-selling O'Reilly book, Developing Web Applications with Haskell and Yesod. We're so excited to have Michael with us today to present this webcast for you all. I will turn the program over to Michael in just a moment, but first I'd like to go over some housekeeping things to help you get the most out of today's webcast. You'll want to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Michael. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Michael, please preface them with a capital letter Q so we know that they're for him and we can make sure he sees them for Q&A. You can also open, move, and resize any of the other widgets. If you'd like to tweet from the Twitter widget today, you may need to give it permission to access your account. It will automatically append the event's hashtag to your tweets so you don't have to. And our hashtag today is Haskell, all one word. If you should have any problems during the event, please take a look at your help widget. If you continue to have problems, please post it in the chat room and one of our staff will help you right away. For choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is to close any apps that could interfere. People always ask, so we'd like you to know we are recording today's webcast and we'll have an archive ready usually within 48 hours. And folks, at this time it is my pleasure to turn the program over to Michael for his presentation. Hello, Michael.
Hi, Yasmina. Thank you very much for the introduction. And hello, everyone. I'm Michael Snoyman. I'm going to be speaking with you today about domain-specific languages and designing them with the Haskell programming language. So to get started, we should address the main question. What is a DSL? So obviously, we're not talking about an internet connection here. We're talking about some kind of specific programming language designed for a narrow problem domain. The flip side of a DSL would be a general purpose programming language. That's the kind of language that we program with in general. So Haskell, Python, Java, these are all programming languages which can be used to solve just about any kind of programming problem out there. On the flip side, a DSL will be designed to solve one very specific problem. So that begs the question, why should we even bother with creating DSLs? If all these are capable of is handling a smaller subset of problems, it seems like we shouldn't even bother with them. We can just use our general purpose languages to address all of our problems and disregard DSLs. The advantages of a DSL, though, are since it's focused on a specific domain, oftentimes the code that you produce with them can be much shorter, and as a result of being shorter, much easier to read than general purpose code. In addition to that, you can design a DSL in such a way so as to limit the power available to users. By doing so, you are able to prevent users from creating overcomplicated code, and in certain cases, you can also provide a measure of security. The prime example of that would be in some kind of templating language. Instead of allowing a user to perform arbitrary actions, firing the missiles, accessing a database, they can only deal with a subset of code, which means you don't have to worry so much about, say, your web designer messing up your web application by putting in something invalid into your HTML template. DSLs can also be designed to enable declarative programming. So instead of stating how you want to splice a few strings together to create your HTML template, you just say what you want the result to be, and the DSL itself will figure out how to put it together. Or to take a more practical example, perhaps, with regular expressions, instead of saying exactly how you want to loop over the characters in a string, say, I want to match 3 digits, and the regular expression engine is able to figure it out for you behind the scenes. And finally, we're able to lower the barrier to entry to writing code by using DSL. A developer, a user, doesn't necessarily have to have a full understanding of all of the moving pieces. By focusing on a much narrower domain, they're able to still be part of the programming process. This, again, coming back to the HTML template example, is very powerful. You can have a designer who really knows nothing about your programming language. If you're writing an application in Ruby on Rails, for example, you could still have your web designer write in a language like less to generate CSS. Give an example of, actually from the Haskell world, of a DSL. We have two sister libraries, XML Conduit, which is a library for parsing and rendering XML content, and XML Hamlet, which provides a DSL for XML generation. So at the bottom of the screen, you can see we've gone ahead and, with the raw data types and the data constructors from Haskell, from this library, we've created some XML content. We've explicitly stated we're going to create an element, and inside that element we want to place another element named bar, and inside that we would like to place a content node saying hello world. And there's a lot of syntactic overhead here. We're explicitly having to state we want an element. We have to use empty to indicate that we don't want any attributes. We have to have square brackets in order to indicate that we have a list. And there's a lot of syntax here. On the flip side, in the top, XML Hamlet really lets you get right to the point. We have an element foo. We indent so that we're indicating that bar is inside of foo, and bar is another element, and it contains the text hello world. So in my opinion, the first one is much clearer than the second one. So if DSLs are such a powerful tool, we should in theory use them for everything. What are some of the downsides of DSLs? So the first one is, if you're dealing with a problem domain which is too wide, then you should just go ahead and use a general purpose language. By the time you finish throwing in all of the extra features that you need for this problem domain, you're going to end up with a badly designed general purpose language. One example one might be able to make is in a web development setting. In the Yesod world, we've created a web framework based on Haskell. An alternative might have been to create an entirely new language specifically tailored for web development. But by the time you end up throwing in all of the different components and DSLs necessary for web development into a new language, you basically created a full-blown general-purpose language without all the tooling, without all the experience that comes from using an existing language. So if you're going to go for something which is so wide, a problem domain which is so wide, just go ahead and use Haskell, use Python, use whatever general-purpose language you're already comfortable with. A more subtle point is DSLs can be looked at as a trade-off between power and elegance. General-purpose languages provide you full power. You can do whatever you want, whereas DSLs give you an extra level of elegance. Now, depending on your specific needs, this trade-off may or may not be a good thing based on what the languages that are available to you. So hopefully this talk will give you a bit of an idea of the different trade-offs available so you can make an informed decision when the time comes. And something else to point out is that as a DSL becomes more separated from the host language, these points become a lot more important. So on the one end of the spectrum, a DSL which is very closely related to the host language would be regular expressions, especially in a language like Perl. If you're in Perl, using a regular expression is very easy, and then immediately pulling back to Perl code is also very easy. So if you run into something which is beyond the scope of a regular expression, it's very easy to go ahead, drop down from that, and go back to regular Perl. Perhaps at the other end of the spectrum, you have languages like XSLT. In XSLT, the DSL is much more separated from the host language. And so it's still possible to have interaction between the host language and the DSL, but it takes much more work. And as a result of that, the questions above become more pertinent. But the most important rule about DSLs is don't abuse them. If you have a DSL such as regular expressions, use them for parsing things regular expressions were meant to parse. Don't use it for parsing HTML. If you need to process HTML, if you need to parse XML or JSON, use an existing parser. There's no reason why you should try to fit Just because you have a hammer, not everything is a nail. Same thing, XSLT. It's a language designed for XML transformations. If you try to do a bunch of other things that it's not designed for, you're going to have a very difficult time. All right, so assuming we're at a point now where we understand what a DSL is, we understand why we want to use a DSL, the question is, how are we going to write our DSL? We have to have some kind of a host language, which is going to allow us to create the tooling to use this DSL. So the point of this talk is Haskell makes an almost ideal host language for DSLs for many reasons. So just to run through an overview here, and we'll get into details throughout the talk, Haskell has a very nice syntax already. We have a lightweight function application syntax, as opposed to the C family of languages where you have to use parentheses to apply functions. In Haskell, simply placing two identifiers next to each other automatically implies function application, which means you can actually strip out a lot of the syntactic noise involved in using functions. Another feature, which is very powerful for DSLs, is that we have arbitrary operators. In C++, you're able to overload operators. You're able to take operators that already exist in the language and redefine their meaning for specific types. Haskell allows you to create entirely new operators whenever you want. And this can be problematic. This can turn the language ultimately into line noise. So this isn't a feature that should be abused. But in the context of a DSL, it does allow you to create much terser code. Some of the DSLs that we'll be talking about involve breaking out entirely from the Haskell syntax. This is quasi-quoted, the kind of quasi-quoted or template Haskell-based DSLs. The fact that Haskell has built in very nice parsing libraries, especially Attoparsec, parseArgs, to be able to parse things easily, means that you can go ahead and whip up a new syntax without a huge amount of overhead. Since Haskell is statically and strongly typed, we're able to catch a huge amount of mistakes in the DSL at compile time instead of having those errors deferred to runtime. A lot of the time with regular expressions or with XSLT, the two examples I've given so far, those kinds of errors really only pop up at runtime. In Haskell, we can force a lot of errors to show up at compile time. We have a lot of overloadable syntax in Haskell itself. So for example, do notation. Do notation is available for any kind of monad. This can be used for many different purposes, for creating parsing libraries, for creating HTML combinator libraries, or even data serialization. Anything which is a monad automatically inherits do notation. We have an overloaded string syntax, so that you can use string literals to mean different things. Numeric literals have existed for a while, and hopefully in one of the upcoming versions of GHC, we're also going to have an overloading for list syntax. So this ability to take a built-in syntax and reuse it for something else is very ideal for DSLs. Finally, we have this combination of template Haskell and quasi-quotes, which allows us to generate code at compile time, let that code be type-checked and compiled by GHC itself, meaning we get all of the optimizations, all of the built-in performance enhancements of Haskell, the language itself. Okay. So now, as far as the categories of DSLs that we can implement in Haskell, this is my breakdown. I'm sure other people will have other ways of looking at this. But I really look at it as three categories. In the first category, we have a DSL, which is actually just Haskell code. A lot of people might call this an embedded DSL. This is where we're using normal Haskell syntax. We're providing a special set of functions, perhaps some kind of operators for convenience. But at the end of the day, we're just creating a normal Haskell library. It's almost at the point where you wouldn't even call this a DSL. A step beyond that is to use something called overloaded strings to be able to take normal string literals and turn them into something else. And within those string literals, you can really embed some kind of arbitrary syntax. That's a very limited form of parsing, since it all has to be within a single literal, and there's very little type checking. Going a step beyond that is where we allow fully arbitrary syntax via quasi-quotes. So people familiar with the Yesod world will recognize, for example, Hamlet. Hamlet is our HTML templating system. We have a fully arbitrary syntax not based on Haskell at all. All right, so let's step through some examples of real-life Haskell DSLs, starting off with the first category that I mentioned in pure Haskell. Attoparsec is a commonly used library. It is, instead of a parser generator, it's actually a parser combinator library. So what you're seeing in front of you is just normal Haskell code. We're using do notation, and we have a whole bunch of specialized functions, named functions, string, skip space, take till. This is just a normal piece of Haskell code. There's nothing magical going on. We have decimal, a few other things. Let's go ahead and look at a little bit of an explanation of this. Because we've stayed in pure Haskell, we're able to leverage the full extent of existing Haskell infrastructure. All of the combinators that already exist in Haskell, type classes, the monads that I mentioned, but also applicative and alternative type classes provide a lot of combinators, a lot of operators that from the Haskell world you already know how to use. So as a result, you can learn those type classes and get to use them in a number of different DSLs. The basic idea is that in order to create one of these DSLs, you create some kind of special data type. In the case of Attoparsec, the data type is parser. And you just provide a bunch of functions for interacting with it. So at this level, we've really hardly even touched the surface of being called a DSL. Let's take this just a little bit of a step further to the ISON library, which is probably today the most popular JSON library in the Haskell world. And we have these two type classes. Again, we're able to leverage a lot of the existing infrastructure of Haskell. In this case, we have two JSON and from JSON type classes to indicate how a data type would be encoded, serialized and deserialized from JSON. So again, this is very similar to the Attoparsec example that we were looking at previously. We have functions such as the object function. In this case, we've also thrown in some new operators. So we had the dot colon and the dot equals operators, which were used for parsing and rendering, respectively. And we were able to use the existing type class infrastructure, in this case applicative. Let's go back to the code to just have another look. So in this case, you'll see that on the last two lines of the screen, we're using the applicative operators in order to parse out the name and the age and automatically apply the person data type to those instead of having to use a much more heavyweight monadic form, which would involve having to create temporary variable names. So this, again, gives a nice lightweight feel to our DSL. Still in pure Haskell, but starting to feel more like a DSL. The dot equals is specifically designed for ASON, and therefore takes us a little step further from normal Haskell code. Moving, again, just a little bit further, let's go into the concept of XML cursors. Cursors in this context are a means of traversing an XML tree. So consider this fairly simple HTML document. And let's say that we want to extract the title of some section. With XML cursors from the XML conduit library, we're able to do that with a few specialized operators. We have our initial cursor. We then, with the $// operator, we find all descendants of that cursor, which are elements named section. We then take all those section elements and we filter them down to all the sections which have an ID attribute, which is equal to section ID. We find all the children elements thereof, which are H1s. And then we find all the descendants from there, which are content nodes. So you can see in these 4 or 5 lines of code, we're really expressing a lot of different statements. Our use of operators in this case really allows us to state a lot of information. This could be done without the operators, but it would make the code much longer. let's talk out some of the pluses and minuses. We've designed the library around XPath. XPath is a standard for querying XML documents. So a lot of the operators, the // for example, lifted directly from XPath as a means of finding all descendants. Named functions such as element and attribute is are used for the common activities that don't fit into the operator into the set of operators. So the named functions make it much more clear what's going on. Most people can look at element h1 and get at least have some kind of a feeling that we're doing something to find elements named h1. So in that sense, the named functions are much easier for beginners to get started with. The operators, on the other hand, may make it more difficult for a beginner to use the library. So this is actually an important trade-off to point out. As you become more operator-heavy, it means that the code will become terser, which is good for experts, but it does mean that you have a higher ramp-up cost for new users getting used to things. Now, the library itself is built around the central concept called an axis. An axis is just a function which takes a cursor and returns a list of more cursors. So in the case of children, the child axis would take a parent cursor and return all of its children. The element axis, on the other hand, is just a filter. So it will take a single cursor and return either 0 or 1 cursors. The original cursor if it matches the element name given, or nothing if it doesn't exist. The important thing to point out is that this has been built on top of normal lists. Lists are a very strongly supported data type in the Haskell world. We have a built-in monad instance. We have list comprehensions. By sticking to well-supported data types and building on top of them, it means that all of the existing infrastructure that we have is at our fingertips. We actually have an example of that in the code itself. On the line that includes attribute is, the operator on that line is the monadic composition operator. We're just using normal monadic composition for lists in order to put these two axes together. That's because we're able to leverage the existing type class infrastructure provided by lists. Okay. And finally, let's just have a quick run through of some of the other operator approaches. In the Yesod world, we have a form processing library, which was ripped off entirely from the formlets library that preceded it. With form processing, we use applicative functors to a great extent. So the line of code you see there, person, text field, age field, it's slightly simplified from what we actually have because we have a few more settings that need to be applied. But it does get across the point. We're able to declaratively state that we want one field which is going to be text, one field which is going to be age or an integer, and we want to take these two things and put them into the person. This is a drastically simplified approach versus many other form libraries that are out there. Another example is the conduit family of the conduit package, or also enumerator and pipes packages. These are packages that are meant for dealing with streaming data. For example, opening up a file and getting a stream of the bytes coming out of that file. In this case, we have some operators which are intended for connecting two different components together. So that line of code you see would read a file named input, connect it to the gzip conduit, which would compress all of the data, and finally, that would be connected to the sync file, which would store the data in output.gz. This line of code is a fully functional piece of code, which if you use it in your Haskell code, would actually compress input into output.gz. So you can see, using these operators in this way really does make it possible to express a lot of information in a few words. And just to summarize, I think I mentioned most of these points already, but to go over some of the downsides of operators. Every time you use an operator, that's something new that a person has to learn. Named functions are much easier to pick up. You can usually use a named function and have people have a basic understanding of what's going on. For example, source file in this page may not be completely clear, but you have the idea. We're going to get some kind of data from a file. The $$ operator, on the other hand, to someone who is not familiar with conduits or enumerators, really would have no idea what's going on there. So It does present a barrier to entry for newcomers wanting to use and read code. But once you learn them, hopefully the investment pays off. On the flip side, if you use common operators, like the applicative operators, these are functions, these are operators that are already well known in the Haskell community, and therefore it won't be such a shock for people coming in. Okay. Yeah, and let's cover this slide, and then we'll take a break for questions. All right, so I mentioned that middle category of DSLs was using overloaded strings. I'm not actually going to focus on that too much. I just wanted to give some basic examples. One package that I end up using quite a bit is the system file path package, which provides an abstract data type for representing paths. So instead of just dealing with paths as a string, we actually have some data type that hides that information. Now, of course, I would like to be able to type in some file.txt into my source code. If we didn't have overloaded strings, you would have to manually convert from the string to the file path. But because of overloaded strings, that string literal can immediately be understood as a file path. When you combine that with some convenience operators, like the slash and dot operators you see there for dealing with subfolders and dealing with file extensions, this actually can make your code very easy to read. Another example is the XML types package. It provides a name data type to represent element and attribute names in XML. XML names are a little bit more complicated than just a piece of text because they contain both a namespace and a local name component. So the overloaded string version of name will recognize something called Clark notation. So this first string you see is just a normal local name without any kind of a namespace. But the second one, since it starts off with those curly braces, is understood to have a namespace of some namespace and then a local name of local name. The problem with this instance is that if you provide it invalid input, there's no way at compile time to check if the input is invalid. And instead, things will blow up at runtime. So some people think this is a major downside of overloaded strings and therefore avoid it. Other people consider this to be an acceptable trade-off. A final example is there's a web framework called Scotty. It's designed to be a lighter weight framework than Yesod. So, for example, Scotty is to Yesod as Sinatra is to Rails in the Ruby world. In Scotty, routing is performed by using overloaded strings. So in this example, you see that we're going to perform a GET request, and it's going to be /some word, and that value will be stored in the word parameter. The problem with that versus Yesod is that you don't actually get a lot of compile time checking. We don't know what the data type of word should be. We don't get it checked to ensure that it's, say, a valid integer. On the other hand, with Yesod, you do get it. But Scotty's approach is definitely a much more lightweight approach, which is easier to implement and easier to understand. Okay, are there any questions at this point?
Thank you, Michael. Let's take a peek here. And folks, as you heard, we are at a point where we can take questions. So if you do have a question for Michael, please open your group chat widget, type it in, send it in, and he'll answer it while he's with us. I am not seeing any questions yet, so we'll turn it back to you, Michael.
Okay, cool. All right, so we've covered the first two categories of DSLs. Let's move on to the third, the outside the range of Haskell itself. One of the examples that I probably deal with most on a day-to-day basis is Hamlet. This is an HTML templating language based on whitespace, very commonly used in the Yesod world, also used outside of Yesod quite a bit. Some of the things to point out here, you'll see on the fourth line where we use title, there's actually that hash with curly braces and then the word title. That's referencing directly a Haskell variable. Also, when we have the for all line, we refer to the people variable, and we loop over all of the values inside people and place them into this person constructor with name and age. So let's talk a little bit about this kind of a DSL of Hamlet. The syntax is completely free form. We can make it whatever we want. Hamlet has its own parser based on parsec, and therefore, we're not tied to Haskell syntax anymore, which is definitely liberating. We don't have to worry about collisions with keywords. We can go ahead and use white space and angle brackets to get something which feels much more like HTML. Hamlet itself will take your template and convert it into Haskell code. This means that everything is type checked. So in our previous example, we had that people variable. If the values inside people aren't actually persons, then the code won't compile. It will fail at compile time and tell you that you have a type mismatch. And this is a huge strength, because well, if you're from the Yesod world, you definitely feel this way. A lot of people in the Haskell world, that you should catch as many errors at compile time as possible. Also, since we're dealing with Haskell code, we're able to deal directly with the Haskell variables via our variable interpolation, which means we don't have a very high overhead for using these variables. We don't have to declare some kind of wrapper. We don't have to manually pass in our variables. Some downsides of Hamlet definitely come in on the implementation side. As opposed to some of the other examples we gave, it takes a lot more work to implement something like Hamlet. You have to write your parser, and then you have to write your code generator. Code generation comes down to writing Haskell code, which produces Haskell code, which produces an abstract syntax tree of Haskell via template Haskell. So that can be difficult. That can definitely be error prone. So Hamlet itself comes with a very large test suite to make sure that it works correctly. So the idea here is that on the implementation side, Hamlet can be something difficult to implement, but on the usage side, you can rest assured that as long as that it's implemented correctly, you're using a powerful tool that should be pretty easy to use. Hamlet, because of the way it's been designed, is actually very good for working with non-programmers. We have reports from Yesod usage in industry where HTML designers are writing the Hamlet templates themselves. There's no need to get a developer involved in the process. If we were using a DSL, which was inside Haskell code, that probably wouldn't be possible. It would be much more difficult to explain Haskell syntax to a non-developer and make sure that the non-developer isn't accidentally writing some dangerous code, as opposed to using Hamlet, which is a purposely limited language and doesn't allow a lot of the dangerous activities that could happen inside Haskell itself. In order to use Hamlet, I had mentioned earlier that we have quasi-quotes in template Haskell. So let's look at first at the quasi-quotes. We have this thing with the square brackets and the pipes in between. That's a quasi-quotation bracket. Inside that bracket, the h1 hello name, that is a completely free syntax which is not touched by GHC at all. The compiler ignores it and passes it on directly to the Hamlet quasi-quoter. And this way, you're able to embed whatever syntax you want inside your Haskell code itself. Another possibility is to put your Hamlet code in an external file. So you could create a file called hello.hamlet, place the exact same content in that external file, and then use the template Haskell splice based on Hamlet file to load up that file. At compile time, that file will be opened up, parsed, and then turned into Haskell code. Another example of a freeform of a quasi-quoted DSL is the routing code for Yesod. This is how we generate our, you could look at it as our sitemap, exactly what routes are available in our application. So a lot of people with Yesod are probably familiar with this already. I don't want to dwell too long on exactly what's going on here, but let's take the first line as an example. We're saying that at the root of our application, / we want to create a route named home_r, and it answers GET requests. On the next line, we're saying we want to answer at /fib/ some kind of integer with a route named fib_r, and also we want to answer GET requests. What's nice to point out here is that that information about an integer is now encoded in in this template itself, as opposed to when we had the overloaded syntax example from Scotty earlier, where you can't actually say very much about the types involved. Let's see exactly what's going on with this code. We have a very specialized syntax, very much like Hamlet. And it expresses a lot of information concisely. I might argue that there's not really any superfluous information available in that template. Everything that's there needs to be there and is giving useful information. There's no syntactic overhead. The routing is completely declarative. There's no point at which we're saying how I want you to parse routes. I don't need to know that information. I'm telling the compiler to deal with this. The compiler is going to figure out a way to do the parsing. Turns out under the scenes, we actually use a fairly sophisticated routing algorithm based on vectors and maps to do efficient lookups. But that's completely transparent to the user. The code itself actually generates a fairly large amount of boilerplate error-prone Haskell code. We end up generating 4 different components. We generate a data type, a parsing function, a rendering function, and the dispatch function. Now, if you were writing that manually, you'd have to make sure that all 4 of those match up with each other perfectly. If you accidentally had a distinction between your rendering code and your parsing code, that would just lead to a runtime bug. So by using this kind of a quasi-quotation, we're following the don't repeat yourself principle. The minimal amount of information is there. It's stated once. And then at the DSL level, we're taking responsibility to make sure that we're generating the correct code. Now the downsides of this, again, the first 2 really are on the implementation side. You have to write your own parser again, which in this case really isn't such a big deal. The syntax is pretty simplistic, so the parser is very simple. But more complicated is generating these data types and these functions. In the Hamlet example, it was very much a one-to-one representation between the Haskell code and the Hamlet code. It's pretty easy to explain to someone how we're going to take that Hamlet code and turn it directly into a function which will generate text. In this case, it's more complicated, and it takes more work to implement. Generating the data types and the functions correctly is difficult. And again, we rely very heavily on unit tests to make sure that the code we're generating is correct in all cases. From a user perspective, getting to this level of a DSL is very convenient. They're able to get a lot of work done very quickly, but sometimes it can be intimidating because now you're dealing completely with a black box. You don't know, someone who hasn't actually read the code may not have any idea what's going on behind the scenes with this DSL, and that can be a bit scary for users. We're trying to overcome that in the Yesod world by making the documentation clearer to explain exactly what's going on. And I think, in general, I think this trade-off is a good one, as long as the documentation is available so users can feel confident that they have an understanding of what's going on. Okay, are there any questions at this point?
I will check for you. No questions yet. Again, folks, you have that group chat widget. If you do have a question for Michael and what he's talking to you about, please click on it, open it, type it in, send it in, and he will answer it while he's with us. Back to you, Michael.
Okay, thanks. All right, so the final section of this talk, I actually wanted to step through a real-life example of creating some kind of a DSL. What we're going to create is a very simplified command line parser. Now, a lot of this is going to be built around the idea of creating data types and creating proper instances for those data types. So let's start off with a base type for representing results. Our parsing could succeed or it could fail. And if it fails, it could fail with a set of error messages, 1 or more. So that's what our data type up at the top represents. We have a result. Error could be a set of texts, or we can have a single success. I don't want to go too into detail with the explanation of what applicative functors are, but here are the implementations of the basic type classes of functor and applicative. And essentially, we're just going to go ahead and take all error messages that exist and combine them together. And if we have a success, we'll pass on the success instead. One extra instance that we want to implement is alternative. If we have two different results in front of us, and we would like to choose whichever one of them succeeded. So if both of them failed, we'll take the error messages from both. And if the left one succeeded, we'll take the left one. And if the right one succeeded, we'll take the right one. Now that we have this result data type, we can build a command parser data type on top of that. So we'll have this helper type args, which will be a dictionary, a hash map from the argument names to the argument values. And then this command parser is going to be the core of our DSL. Command parser is going to be, it's just a new type wrapper around a function which takes the arguments on the command line and returns some kind of a result. This new type wrapper is important. Since we're using the new type wrapper, it means we can go ahead and create whatever instances of this new type we want, which we're going to do in a moment. The core of this is that function going from args to result. Because really, you can represent any kind of parsing with that piece of information. If you know what the arguments were that the user provided, you can go ahead and parse that and get the result. So again, we have this functor and applicative instance. This is actually built on top of the functor and applicative instances that we had for the result data type. And again, we create an alternative instance. So we're able to say, I would like to try either one of these parsers and take the results of whichever one succeeds. parseArgs, I don't want to dwell on this function very much. This is just a helper function for parsing out the arguments from the command line. We're going to follow the very common syntax of -- name followed by the argument value. And once we have that parseArgs function, we're able to create something which would run a command parser. So we have that command parser, which again is which is the core of our DSL. But it's really just a function underneath the surface. So we unwrap that new type wrapper, and we get this function, which essentially is coming from the user. We parse out the arguments, and then we apply the user-provided function to those arguments. If it succeeds, we return the value. And if it fails, we're going to print out all of the error messages and return an error message. And finally, we need to have, two slides left. We have this fromArg type class to abstract over the idea of some value which could be read from the command line, which means we need to represent different things that could be parsed from text. The advantage to this is if we use a type class, we're able to minimize the number of names, the number of functions that need to be provided by our DSL. So fromArg is going to take some text and return either an error message or the parsed value. So we have an instance for text, which will always succeed, and we have an instance for int, which will try to parse this as a decimal value. And if it succeeds, it'll return the value. Otherwise, it'll give an error message saying that the integer is invalid. And now, the final combinator being provided by the library is this arg function, which will take the name of an argument and will return some command parser. So what we do here, this is all hidden away from the user. But we're building up a function inside which takes the command line arguments and is going to do a lookup. If the lookup fails, then we say that that argument isn't available. If that argument is found, then we'll go ahead and use the fromArg function from the fromArg type class to try to parse it. If the parse fails, we'll return an error message. Otherwise, we'll return a success. Now we can tie this all together. So that was a fairly large amount of code, but that was an entire DSL right there. This right here would be an example usage. We're defining a data type called Command, which will create an application which has two different commands. Say hello with some kind of text, probably the name, and CalculateAge, which takes two integers. We'll say that that is the beginning and end year that we want to calculate an age for. My parser is a full-blown command line parser now. We're able to say that say hello should parse the argument name, or, and that's the pipe operator over here provided by alternative, or we would like to do CalculateAge, which would require two named arguments, start and stop. Because we used a type class, Haskell's automatically able to figure out for us that when we use the name parameter, that should be parsed as text. When we use start and stop, those need to be parsed as ints. So the correct function is automatically delegated to. There's very little overhead necessary for the user. If we really wanted to go crazy here, we could take this to the next step and create and use overloaded strings to be able to totally get rid of the arg combinator. Personally, I don't think that would be a good idea here, but it could be done. And then we have the usage runCmdParser on the parser provided. Okay. I think there were some questions on that example.
Hi, Michael. We do have a couple of questions. Yes, a couple of questions have come in. Let's take a peek here. A question from Jay. What kind of parsing facilities are supported by Parsec?
So Parsec actually provides just about all the parsing functionality that you would need. Parsec has backtracking. It has look ahead. You can parse any language that you want with Parsec. Parsec also gives user-friendly error messages and can give location information about where things were parsed from. So from that perspective, Parsec is a very nice parser, and that's why we use it for languages like Hamlet and Julius, which we want to be user-friendly. The downside of Parsec is that it's not the fastest parser out there. It works well enough, but if you want to create truly high-performance parsers, then you probably want to bump up to Attoparsec instead. So for example, in the HTTP conduit package, where we're dealing with parsing HTTP data, and we don't really care if the error messages are user-friendly or not, in that case, we use Attoparsec, which is able to deal directly with binary data. It can actually deal with either binary or textual data. And it has almost all the same facilities as Parsec, including the backtracking, including the look ahead. It simply doesn't have as much in the way of user-friendly error messages.
Super. We do have some additional questions, but did you want to continue presenting, or did you want me to give you the questions?
No, I think now is a good time to go through the questions.
Okay, let's do it. We have a question from Erland. Erland says, could you briefly explain how quasi-quoted code gets translated to Haskell code?
Okay. It's a very good question. When you use quasi-quotations, you have a function which is passed a string. That string is the full template provided by the user. You can then take that string and perform any kind of Haskell transformation on that you like. You can parse it with Parsec. You can use normal string functions. You can perform arbitrary I/O. So you could say take that string and pass it to an external function. An external command line tool. You can do whatever you want with it. But at the end of the day, you've processed that string somehow. You then need to turn it into an abstract syntax tree. So the template Haskell library provides a number of data types that represent Haskell code itself. For example, it provides an expression data type, which includes things like literals, or case expressions, or lambdas. So instead of writing your lambda directly, you would use the letE data constructor. Or instead of putting in a string literal, you'd use the letE data constructor. You go ahead and put that all together. There's also some built-in support from template Haskell that instead of having to manually write all of that code, you can write the code and have it converted into the abstract syntax tree for you, which can make some of this easier. But at the core, you're really just using these data types to create an abstract syntax tree. After you've created that abstract syntax tree, you return it from your quasi-quotation, and GHC will take that abstract syntax tree and treat it just like any other code that it parsed itself from a file. So it will then take the AST representing Haskell code, type check it, compile it, turn it into core, and eventually turn it into machine code.
Great. We have another question here from Aaron, and Aaron asks, I am coming from the Rails world. What's the top 3 reasons / benefits to switch to Haskell, Yesod, and take the learning curve?
Okay, so top 3. I'll start off with, for me, the most important one, which is type safety. A lot of people who come from backgrounds with other statically typed languages like Java or C++ believe that a lot of that static type systems don't really give you a huge amount of benefit. And when you're dealing with type systems like those provided by Java and C++, that might be a true statement. The difference is that you're actually, in Haskell, able to represent a huge amount of data at the type level. So an example, which happens to me on the screen right now, is the fact that we're automatically able to choose the appropriate parser for an integer based on the type. There's no need to try to guess which function should be used. The type system can figure it out for you automatically. Yesod goes much farther than that with ensuring that all of your route generation, all your links are correct, and also avoids things like cross-site scripting attacks. For me, that's the number one benefit. Another huge benefit is we have not automatic, but almost automatic access to parallelism and concurrency. And the main reason for that is that by default, Haskell data types are immutable. So instead of having some kind of data which can be mutated at any point in time, you're able to rely on the fact that these values are not going to change. An example that we have right here in this DSL is our hash map. There's no need to worry that some user code might start modifying the arguments and the command line arguments arbitrarily later on. We know that those are set in stone because we have a persistent data structure. I'm not sure exactly what I would put in position 3. Some people might say overall performance. Haskell performs very well. Probably, usually most benchmarks put it on a par with either Java or C++ code. So pretty far up there. There are plenty of other reasons I could give. I think I'll stop it there, though.
Great. This time it looks like that's all the questions I have come in, so we'll turn it back to you.
Okay. So after all that, I'd just like to sum up at this point with a review of what we were talking about today. So when you want to create DSLs inside Haskell, the pure Haskell DSLs, you get a lot of benefits. Users get to still write their concise code, whether it be because you've provided them with a nice monad and nice named functions, or because you've provided them a bunch of convenience operators. Whatever the case may be, their code is going to be more concise. But they haven't really lost any power. So that elegance versus power trade-off I mentioned earlier on doesn't really exist so much in this case. They still have all the power of Haskell at their fingertips. Also, these languages are relatively easy to implement. The command line arguments, if I was able to put it into 5 slides, you can guess it's not really that much code. I think it comes out to about 40 lines of code all told. So you can definitely get these, you can get up and running very quickly and give a lot of power with low overhead. Overloaded strings can be used to avoid a lot of user boilerplate with converting from string literals. It makes it a lot cheaper to have specialized data types. In the Haskell world, we were able to switch over almost completely from an inefficient string representation to an efficient representation using the text package. And that was because you're able to continue using your string literals however you want. Downside with overloaded strings, you don't really get so much compile time checking. One example I gave was the routing with Scotty. Another example is with byte strings, that you can go ahead and represent a sequence of bytes using a string, but if you embed some value beyond the range of what a byte can represent, beyond 255, then you're not going to get that caught at compile time. Finally, if these options don't work for you, if you need something more powerful, you always have the option of going to specialized syntax. It does have the heavy upfront cost because you do have to create your own parser, you have to write your own code generation, and it's non-trivial. And users are not able to take full advantage of Haskell syntax because they are now in your specific language. Looks like the last bullet on that page got lost, or the last two. On the flip side, you do get to have full control of your syntax. And even though you are dealing with a totally different language, due to the way that quasi-quotation and template Haskell works, we still have a nice tight integration with the host language. In the case of Hamlet, you're able to directly reference variables. In the case of Yesod routes, you're able to actually generate data types and functions which will be used through the remainder of your Haskell project. So yes, it's a different language, but it's still very close to the host. So with that, that's the end of the slides. I'd like to thank everyone very much for participating.
Great webcast today, Michael. Thank you so much for presenting it and for sharing all your knowledge and expertise with us. Folks that attended, we thank you for attending and hope you benefited from it. And those of you that sent in your questions, thank you so much. Having those questions just adds that much more to our event, so we do really appreciate it. And to let you know, Michael, the folks that did send in those questions, they all say thank you to you for answering them. They appreciate your clear answers.
Thank you very much. My pleasure.
And also, folks, we want to let you know that we did push out in your group chat, so if you hadn't opened it yet, please do. Good information there to save you some money as a thank you for attending the event. Michael's book, we do have a code in there so you can get Michael's book. If you like what you heard today, lots more good information and tips in there to help you with your day-to-day. So please, we do encourage you to take a look at that. Again, thank you, Michael. Thank you, everyone. This will conclude today's webcast. Goodbye, everybody.